So now that we know the laws of reflection and refraction, let's try to apply them. So in order to do that, I have set up a place where I can have two different media with refractive indices N1 and N2, and then I can also change these refractive indices by moving these sliders over here. I can also change the angle of incidence, theta I, and in this particular case, the angle of incidence is always measured in the first medium, so it'll be called theta 1, and the angle of refraction is, of course, in the second medium, so that's theta 2. Now remember that the second law of reflection tells us that the angle of incidence and angle of reflection have to be the same, right? So if the angle of incidence is theta 1, the angle of reflection also has to be theta 1. Okay, so now let's see what happens in the very simple scenario. We have two different refractive indices, N1 and N2, but the ray of light is incident normally, right? It's normal means perpendicular to the surface. So the ray of light is this red line that's incident over here. As you can see, after refraction is going to pass undeviated, a part of this ray is also going to get reflected. But since the angle of incidence is 0, the angle of reflection is also going to be 0. All right, so now we can ask the question as to what would happen if I change the index of refraction of one of the two media. And you can see that this normal incidence is not affected by the values of the N1 and N2 in this particular problem. All right, so now in this scenario, I will now start changing the angle of incidence, and let's see what happens. You see, as I increase the angle of incidence, the angle of reflection is increasing. And in this particular case, I have chosen the two media such that the medium from which light is incident is a rarer medium, rarer because the refractive index is 1, which is less than the refractive index of the second medium, which is 2.5. So because the second medium is denser, the ray of light is now moving closer to the normal, right? So theta 2 is going to be less than theta 1. Okay, so we can keep increasing this, and we can increase this all the way up to theta 1 equals 90 degrees. Of course, it's kind of pointless to increase theta 1 to larger than 90 degrees because we're saying that the ray of light is always incident from the first material, and you can't go beyond the first material, and hence the maximum value that theta 1 can take is 90 degrees. Okay. And you can see that even for 90-degree incidence angle, theta 2 is some value that is in between 0 and 90 degrees. And in this particular case, we can even work this out. Remember, Snell's law tells us that n1 sine theta 1 is equal to n2 sine theta 2. Okay, so in the situation where theta 1 is equal to 90 degrees, so the angle of incidence, right? This is the angle of incidence, right? And we know that n1 is equal to 1 in this scenario that I've cooked up, and 2 is equal to 2.5. So that will tell us the sine of theta 2 is equal to n1 sine theta 1 over n2. And so this is going to be equal to, remember theta 1 is 90 degrees, so sine of theta 1 is 1, n1 is also 1, so this is just going to be 1 over 2.5. Okay, so that is equal to 0.4, right? So theta 2 is then equal to sine inverse of 0.4, which is somewhere between 0 degrees and 90 degrees, right? So this, we can clearly say that 0 less than theta 2 less than 90 degrees in our particular situation. All right. Okay, so now I want to study slightly different situations. So I'm going to go back to the initial angle theta 1 equals 0, theta 2 equals 0 case, and I want to switch these, the values of the refractive indices. So I want to make N2 be the rarer medium, so N2 equals 1, and 1 equals 2.5. As expected, theta 1 and theta 2, if theta 1 is 0 degrees, theta 2 remains 0 degrees, okay? But for any other value of theta, you'll see that there's a dramatic difference in situation. So let's increase theta I here. So if I increase theta I, you see that initially there is a refracted ray over here, right? As expected, because light is now going from a denser to a rarer medium, the ray of light is moving away from the normal, right? So this is the normal. The ray of light moved away from the normal as it entered the second medium. And then if I keep increasing theta, there is a point where there is no longer a refracted ray, okay? And this particular situation where there is no longer a refracted ray is known as total internal reflection. Okay, so total internal reflection can only happen when a ray of light is incident from a denser to a rarer medium. So this is very important, denser to rarer medium. And what does denser and rarer mean? Well, N2 has to be, so N1, which is the refractive index of the incidence medium, that has to be larger than N2, which is the refracted medium. Okay, so if that condition is satisfied, then there are situations where total internal reflection can happen. And what does total internal reflection mean? It means that 100% of the light gets reflected. There is no part of the light that gets transmitted. So if you wanted to think about it in terms of intensities, then intensity of reflected is equal to intensity of the incident ray of light. Yeah, so that happens when total internal reflection happens. No part of the light gets transmitted or refracted through the medium. So let's try to figure out when this happens. Well, I can sort of I can keep increasing theta 1, right? So at initially when theta 1 is 0, theta 2 is also 0. And if I keep increasing this, you see that at some point, theta 2 will reach 90 degrees, right? And this is essentially because of the fact that as you increase theta 1, Snell's law is telling you that theta 2 is increasing, but it's getting more and more, going more and more away from the normal. So at some point that going away from the normal is just going to be equal to 90 degrees. So let's see the point at which this happens. And so again, I'm going to apply n1 sine theta 1 is equal to n2 sine theta 2. N1 sine theta 1 equals n2 sine theta 2. And at some point, theta 2, which is the angle of refraction, becomes equal to 90 degrees. So if theta 2 equals 90 degrees, let's find out for what value of theta 1 that happens. So then we can work backwards and see that theta 1 has to be equal to sine inverse of n2 sine theta 2 over n1. But remember, theta 2 is 90 degrees. So if I plug that back in there, then the sine of theta 2 is becomes 1. So we get sine inverse of n2 over n1, right? So we know in this particular case, n2 is 1 and 1 is 2.5. So this again will happen for the value sine inverse of 0.4. Okay, so this is actually telling us how rays of light are reversible, right? So when I started with a medium n1 equals 1, n2 equals 2.5, I found that if the angle of incidence was 90 degrees, then the angle of refraction would be this sine inverse of 0.4. And now in the opposite case, when light is incident from the medium which has refractive index 2.5, right? The upper medium now has 2.5 and the lower medium has 1 as refractive indices. Then if the angle of incidence is sine inverse of 0.4, then the angle of refraction would be 90 degrees. And you can now imagine that if I increase the angle above, increase theta 1 above the sine inverse 0.4, then the angle of refraction, if I just wanted to use Snell's law, I wouldn't be able to find it, because if I increase theta 1 any further, right, sine of theta 1 would increase, right? So how could sine of theta 1 increase? Well, the only way it could increase is if sine of theta 2 increased, but theta 2 is already 90 degrees, which means sine of theta 2 is at its maximum. So it's not possible to increase the sine of theta 2 anymore, which means just for Snell's law purposes, it's not possible to increase the angle of refraction, or in that matter, angle of incidence any further for refraction to happen. So if refraction can't happen, the only thing that can happen is reflection. So that's why all of the light that is incident at the surface is going to get reflected, and that's what's going on in this kind of a scenario where the angle theta 1 is larger than sine inverse of 0.4, right? Often this angle that we found over here is called the critical angle, right? Critical angle. So critical angle is the angle of incidence above which, when light travels from a denser to a rarer medium, it gets totally reflected. So let's sort of write that down in words. So critical angle is the angle of incidence above which a ray of light going from a denser to a rarer medium will get totally reflected. Okay, and the particular phenomenon will be called total internal reflection, right? So critical angle, and often the symbol for critical angle is theta c, and the definition, theta c is equal to sine inverse of n2 over n1, and you can clearly see that if n1 is larger than n2, then this is meaningful, right? So this is meaningful only if n1 is larger than n2. If n2 was larger than n1, then within the parentheses we'll have a number that is larger than 1, and it's not possible to find the inverse sine of a number that is larger than 1, because sine of an angle cannot be larger than 1. So that's the idea here. That's the idea for critical angle. Okay, so that's critical angle. Let's now talk about a consequence of refraction. So one particularly interesting consequence of refraction is what happens when you look into a pool of water. So for example, over here I have a picture which shows a picture of a ray of light, let's say coming from the bottom of the pool over here. And because this is water, water has a refractive index that is larger than the refractive index of air, 1.33 versus 1 for air. So as this ray of light from the bottom of the pool hits the surface of interface between air and water, it's going to get refracted. And because air is rarer than water, what do you think would happen to the ray of light? Will it go um, will it move closer to the normal, or would it move away from the normal? Well, this picture here shows us that if the ray of light went undeviated, it would go along this direction. And of course, it moved away from the normal over here, right? So that's what is expected as a ray of light goes from denser to rarer medium. It moves away from the normal. So theta 2 here is smaller and theta 1 is larger. And what does that mean? Well, if you placed your eye over here, then you would see this ray of light coming in this direction. But since you can't see anything more, to you it would seem like this ray of light is appearing to come from a point somewhere over here, right? So as if you will see an image of this point at the bottom of the pool to be at this point over here, where the rays of light seem to be coming from, right? So that tells us that you will see this the depth of the pool to be to you, the depth of the pool or an object at the bottom of the pool would appear to be much smaller than it actually is. So that's brings us to the topic of real versus apparent depth. And one can find relationships between these just by working out trigonometric relationships. So, for example, if you look at this picture over here, we know that sine theta 1 has to be equal to n water times sine theta 2, and that's just simply Snell's law, right? Where I have put in n air is equal to 1. So n1 sine theta 1 equals n2 sine theta 2. So here n2 is just n water and n1 is 1. Okay, what else can we talk about? Well, if we look at this triangle over here, right? So that triangle, um, this triangle over here, um, that the angle on this side is equal to theta 1. So if that is equal to theta 1, then we know that this distance, right, this part over here, that's just d tangent of theta 1. Okay, similarly, if I look at this bigger triangle over here, right, if I look at that bigger triangle, then theta 2 is this angle. Okay, so capital D times tangent theta 2 is this distance over here from this first dashed line to this second dashed line over there, right? So then we can say that because this distance, we worked it out in two different ways, they have to be the same. So then we can find this relationship that d tan theta 1 equals d capital D times tan theta 2. All right, so generally real depth and apparent depth problems are exactly the applications of these two kinds of formulae in different various different ways. Okay, so now I want to talk about another problem or issue that we sort of come across with water and um, and air sort of reflection and refraction. So if I put a source of light at the bottom of this pool over here, one can work this out in terms of different problems, but we'll just look at what happens physically. What would happen if I put a source of light at the bottom of this pool over here, and these red light, the red rays kind of show you where the rays of light would go. So if the ray of light is incident over here, it's probably going to get refracted over here. But there is a particular value because the rays of light are incident from denser medium water to the rarer medium air, there's a possibility that at some point, for some angle of incidence, the ray of light after refraction has an angle of refraction exactly equal to 90 degrees. And when will that happen? That's the critical angle for water-air interface. So for water and air, so there we know that theta c has to be equal to sine inverse of n2 over n1, n2 over n1, where n1 is the larger number. So sine inverse of n2 here, n2 is n air, right? So n air is 1 divided by 1.33, right? And this is roughly equal to sine inverse of 0.75. So whatever this angle is, this is the angle for which um, if the angle of incidence is larger than this angle theta c equals sine inverse of 0.75, then the ray of light is going to get automatically totally reflected. And that's what's going on with this dashed line over here and this dashed line over there, right? So then this naturally gives you a range of region for which the ray of light would actually reach outside. So if you were an outside observer, you would see sort of this circle over here that is defined by these two rays of light, these boundary rays of light, which refract at 90 degrees after refraction, go at 90 degrees to the normal. That's where you're going to sort of observe the rays of light coming. And alternatively, if you think of somebody that is at the bottom of this pool looking outside, for example, a fish, if it's looking outside, it's not going to be able to see anything over here, as in there is not going to be any rays of light coming from here, being incident here, and can reach the fish's eye. It can only see anything that is inside sort of this circle of radius r. And how do we find the radius of that circle? Well, we just look at this picture and we know that if this angle is if this angle is theta c, or this angle is theta c, then the angle of refraction is 90 degrees. So we also know then that tangent of that angle, tangent of theta c in this particular example, is equal to r divided by the depth of the pool, which is in this particular case, which can be given to you. So r equals tangent of theta c multiplied by d. Okay, and in order to find tangent of theta c, we can just take theta c from here and plug it in. So tangent of sine inverse of n2 divided by n1, right? And this quantity multiplied by d, that's our radius of the surface through which a fish that is placed over here can actually see anywhere outside. So another interesting consequence of refraction is what happens to different colors of light when they enter into a prism. So generally, a prism is this triangular shape like this, right? And let's say I've made a prism out of glass and I have a ray of light that is incident over here. And let's say this is just a monochromatic ray of light, which means it has only one color. Let's say it's the color red. So after incidence, after this ray of light enters into glass, because glass is a denser medium, um, so this is air, that's glass. What's going to happen to the ray of light? Well, it's probably going to move toward the normal because glass is denser. So it's going to move toward the normal like this. And then at the second point now, the ray of light is moving from glass into air. And so it's denser to rarer, so it's probably going to move away from the normal. And so the effect of this kind of a scenario for a prism is that the final ray of light has a deviation compared to the initial ray of light, right? So this is the deviation. Often this deviation is referred by an angle delta, the angle of deviation of the ray of light as it passes through. Okay, so the interesting consequence of having different colors of light is that different colors of light have different wavelengths. So for instance, red has wavelength 660 nanometers, violet has wavelength 410 nanometers. And it turns out that the speed of different kinds of light is also not the same in um, different media. So for instance, in air or in vacuum, all colors of light always travel with the same speed. C equals the speed of light in vacuum, which is 3 times 10 to the 8 meter per second. That's independent of what color of light you're talking about. But as light goes into a different medium, there it turns out that the speeds are different. So for instance, V violet, the violet light actually finds it more hindering to travel through glass than red light, right? So because the speed of violet light is less than the speed of red light, that also tells you that the refractive index of glass for red light is actually smaller than the refractive index of violet light. And so if the refractive index is larger, that means that the ray of light after refraction is going to bend more. And in this case, going from the rarer to the denser medium, it's going to bend more toward the normal. Okay, and then again, when it's going from the rarer to the from the denser to the rarer medium, it's going to bend more away from the normal. And so the effect of this is that when a ray of white light meaning light that contains all colors, all visible colors of light enters into glass, it kind of splits up into different colors because the different colors move at different speeds. So they bend relative to the normal, they bend at different angles. And so these split up, and when they exit out of the prism, it's the same case. They are still split and they're moving, their deviations are different from each other. So eventually what we find is that there is an effective angle of deviation for each color, and that angle of deviation is different. So this is a great way of splitting up white light into its constituent colors. And so that's done through a prism like this. And it's an interesting consequence of essentially the idea of refraction.